For our last example of limits at a real number, we want to show that a limit does not exist. So this is our fourth example, and we want to show that the limit as x approaches 2 of x squared plus 4 over x minus 2 does not exist. And we can use this, we can prove this using the theorem that discussed that if a limit exists, then creating a subsequence or a sequence that converges to 2, evaluating the function on that sequence gives us a new sequence, and that must converge to the same thing. So if I can find two sequences that do not converge to the same number, then this limit must not exist. So let's call this the limit as x approaches 2 of f of x for clarity in what we'll show shortly. So let's consider two sequences. With terms given by a sub n. The first sequence is n plus 1 over n. Sorry, not n plus 1 over n, 2 plus 1 over n. That makes more sense. Now this is a sequence that converges to 2, the value we're taking the limit at. The other sequence we want to be b sub n is equal to 2 minus 1 over n. This also converges to 2. And we'll find that when we evaluate the function f at each of the a sub n values, that new sequence would converge to something different than doing the same thing with bn. All right. So then, the limit as n goes to infinity of f of a sub n is equal to the limit as n goes to infinity of n plus 1 over n squared plus 4 divided by n plus 1 over n minus, and again I said the same thing that I made the mistake of earlier, that's 2 plus 1 over n and 2 plus 1 over n minus 2 in the denominator. Expanding the numerator and simplifying the denominator gives me the limit as n goes to infinity of 4 plus 4 over n plus 1 over n squared plus 4 divided by 1 over n. I can multiply the numerator and denominator by n squared to give me that this is equal to the limit as n goes to infinity of 1 over n squared becomes 1, 4 over n becomes 4n, and 4 plus 4 becomes 8n squared. The denominator simply becomes n. Now we have a familiar limit that we can evaluate without any concerns, and this is infinity. No question about it. So let's take the limit also as n goes to infinity of f of bn, which would be the limit as n goes to infinity of 2 minus 1 over n squared plus 4 divided by 2 minus 1 over n minus 2. Again, expanding the numerator and simplifying the denominator gives us the limit as n goes to infinity of 4 minus 4 over n plus 1 over n squared plus 4 divided by 1 over n. So it's a very similar looking limit. But we will find that there is one distinct difference. So this is the limit as n goes to infinity. Multiplying the numerator and denominator by n squared gives us 8n squared. And actually I made a mistake in copying here. So let's get the numerator, 8n squared minus 4n plus 1 divided by, now my mistake here was 2 minus 1 over n minus 2. The 2's cancel again, but this should be a minus 1 over n. So this is a minus n. So our numerator overall stays positive, but the denominator is going to end up being negative. So this has a negative overall value, giving us a limit of negative infinity. So our two sequences do not have matching limits, so the limit must not exist. Hence, the limit as x approaches 2 of x squared plus 4 divided by x minus 2 does not exist. And that's all we have for this section. I hope you guys have found enough information to be confident in your homework. Of course, you should see, whether it's from me or any other instructor, some examples that reach beyond these ideas. Not significantly, but always remember to take a look at your textbook, whichever textbook that is, and supplemental resources as well. If you guys have any questions, of course, feel free to contact me, and I look forward to seeing you guys soon. Have a wonderful day.